In this video, I will do an example for the Lagrange multipliers. The question says use the Lagrange multipliers to maximize the function minus x ln x minus y ln y subject to the constraint x plus y equals to 1. Well, to start with, you have to remember that we have to write the constraint in the form that everything is left hand side and the right hand side is equals to 0. Then in that case, the constraint, the left hand side, we put it as gxy. And then the Lagrange multiplier method says that first, define this function f x y lambda to be fxy plus lambda gxy. Well, in this case, it means that our function, the capital F or Lagrange function, is minus x ln x minus y ln y plus lambda times x plus y minus 1. Then step 2, find critical points of capital F. Well, it means what? Means that we have to find fx, partial derivative of x with respect to f with respect to x, partial derivative of f with respect to x, and partial derivative of f with respect to lambda. So for the x, I have, well, this term, so we are trying to differentiate. Let me just write it here. dx of x ln x. Well, I'll differentiate that. The other part is only in terms of y. So this is in terms of y. So its derivative with respect to x is 0. Plus the third part, you see this part here, if I multiply lambda inside, I get lambda x plus lambda y minus lambda. And if I differentiate this with respect to x, I just get 1 lambda plus 0 minus 0. In other words, this is the whole thing. But to do this first part, I need to apply the product rule. The derivative of first one, which is 1 times ln x. There's a minus sign outside, minus. The first one itself times the derivative of the second one. The derivative of ln x is 1 over x plus lambda. Well, this gives me, see, this cancels with that, and then we get ln x minus 1 plus lambda. So that is the partial derivative with respect to x. How about derivative with respect to y? Very similar computation shows that I have 0 first term. The second term, it will go exactly the same way, but this time for y. Then the third term is going to be 0, then lambda minus 0. And that will give us minus ln y minus y 1 over y plus lambda, and that is minus ln y minus 1 plus lambda. That's fy. And then f lambda, remember f lambda, we are going to set it equal to 0, and there's lambda here. There's only 1 lambda, and it is multiplied to the whole gxy. So f lambda is always equal to gxy. In this case, it is equal to x plus y minus 1. Well, these are partial derivatives, but we have to set them equal to 0. If x equal to 0, if y equals to 0, and if lambda equals to 0. That gives me 3 equation minus lambda x minus 1 plus lambda equals to 0 minus lambda y minus 1 plus lambda equals to 0. And then the last one, remember, that always gives us the constraint itself. So how do we solve this? Use two first equations, write lambda in terms of x and y. So the first one gives me 1 plus lambda x, 1 plus ln x, and the second one gives me lambda is equal to 1 plus ln y. While these are the same thing, so the left hand side are equal and the right hand sides are going to be equal too. So that means that I can write one equation. I eliminated lambda and I have now an equation for x and y. Well, let's just do this a little bit more. Ones cancel and then I get ln x equal to ln y. Then we can exponential both sides and get x equals to y. Very nice. So we found now this equation here, and we have another equation which is the constraint, and we haven't used it before, so it's time to use it. So we write these two equations together. X plus y minus 1 equals to 0. Then this, plug in this there. This gives me x plus x minus 1 equals to 0. And that means that 2x equals to 1, which means that x is equal to half. And then this and that implies that y is equal to half 2. Well, then we are basically done, because step 3, we are sure that this function has max. The only thing we need to do now is that plug in x and y there. So 1 over 2, 1 over 2, it is minus half of ln half minus half of ln half. And that gives me 2 negative 1 over 2 of something, so that means that we have negative 1 over that, and that negative goes inside. I get ln of negative and appears as power, and that's the same thing as ln 2. So that is ln 2 is the max of that constraint optimization problem. This function is actually is a famous function. It is indeed called entropy function of density, probability densities. But what is important here is that we did use the Lagrange multipliers. Step 1 we defined f, step 2 we find fx, and we find the critical points, and step 3 we plugged into our function.